When the Deep Space Network nearly broke during Artemis II operations, it revealed a hidden truth. During peak mission traffic, spacecraft tracking accuracy is quietly sacrificed to maintain basic communications, leaving some probes temporarily lost in position, uncertainties exceeding 1,000 kilometers. The Deep Space Network reached 80 to 90% capacity utilization during those operations. Controllers faced a choice they don't often discuss publicly: which spacecraft to track, which to let drift in position uncertainty. The network that connects us to everything beyond Earth orbit was stretched to its operational limits, and in those moments of maximum demand, precision became negotiable. We're told the system works with extraordinary accuracy, ranging data with typical precision of 1 to 5 meters for spacecraft position determination, numbers that suggest we know exactly where our distant machines are at any given moment. But systematic errors tell a different story. Solar plasma and tropospheric delays can introduce position uncertainties of 10 to 100 meters. That's the reality behind the precision we advertise. The illusion of continuous knowledge is perhaps the most persistent misconception about deep space navigation. We imagine mission controllers watching screens that show spacecraft positions updating in real time, tracking dots moving across the solar system with unwavering certainty. The truth is more economical, more strategic, and considerably less certain. Spacecraft are often intentionally tracked less frequently during cruise phases to conserve deep space network resources. This isn't a failure of the system, it's a deliberate choice. The network serves dozens of missions simultaneously, and high-precision ranging sessions consume resources that could maintain basic communications with other spacecraft. So during the long months between planetary encounters, when a probe is simply coasting through empty space, tracking becomes intermittent, infrequent, and in those gaps, position errors accumulate undetected. Cruise phase position uncertainties can exceed 1,000 kilometers without frequent tracking updates. 1,000 kilometers, a distance that would span multiple states on Earth, becomes an acceptable margin of error in the context of interplanetary space. The spacecraft continues on its trajectory, following the laws of orbital mechanics, but its actual position may deviate significantly from predicted trajectories for weeks without anyone knowing. The most accurate spacecraft position data comes not from continuous tracking, but from infrequent high-precision ranging sessions. This creates gaps, windows of time where position errors remain unknown to mission controllers. The spacecraft is out there, transmitting, functioning, but its precise location exists only as a mathematical prediction, not a measured fact. The variables that corrupt these predictions are numerous and subtle. Solar plasma near the Sun delays radio signals by up to 100 microseconds. 100 microseconds doesn't sound significant until you calculate what it means for position determination. Those delays create apparent position errors of 15 to 30 kilometers that vary unpredictably with solar activity cycles. The Sun's 11-year cycle of activity means the errors themselves are moving targets, shifting with solar weather that we can forecast but never perfectly predict. Solar radiation pressure pushes against spacecraft surfaces. Outgassing from temperature changes creates tiny thrust effects. These are unmodeled forces, or forces modeled imperfectly, and they accumulate. Spacecraft ephemeris errors grow over time because reality refuses to match our equations exactly. The models are sophisticated, built on decades of orbital mechanics refinement, but they're still models, approximations of a messier truth. Even the ground stations themselves introduce uncertainty. The Deep Space Network's 3 facilities must account for Earth's rotation and plate tectonics. Station position uncertainties of several centimeters affect spacecraft position calculations. The ground beneath the antennas is shifting, moving with tectonic forces, and those centimeters cascade through the mathematics of triangulation and ranging. The Earth itself won't stay still enough for perfect measurement. Doppler tracking residuals in deep space missions often show systematic biases of several millimeters per second in velocity determination. Several millimeters per second. It sounds trivial, but these are errors that translate to position uncertainties growing silently over weeks and months. A velocity bias of 3 millimeters per second becomes 250 meters per day, 7.5 kilometers per month, 90 kilometers per year. The math is unforgiving. Trajectory correction maneuvers become the moment of truth. These planned burns are when controllers discover the spacecraft wasn't where models predicted. The Doppler residuals reveal themselves. Velocity biases that had been accumulating unseen suddenly become measurable when you compare predicted position with observed position during the maneuver. The spacecraft talks back, and its signal arrives from a slightly different location than expected. These corrections aren't failures. They're built into mission design. Every interplanetary mission plans for multiple trajectory correction maneuvers because navigators know the predictions will drift from reality. The corrections are small usually, a few meters per second of velocity change. But they're necessary because the alternative is arriving at your destination thousands of kilometers off target, missing planetary encounters that took years to reach. The capacity crisis makes all of this more acute. The Deep Space Network operates 3 ground stations: Goldstone in California, Madrid in Spain, Canberra in Australia, positioned around Earth to maintain continuous coverage as the planet rotates. 3 facilities serving dozens of active missions, from Mars rovers to Voyager probes at the edge of interstellar space, from lunar orbiters to asteroid reconnaissance craft. During peak mission periods, the network experiences capacity constraints that force difficult choices. High-precision ranging sessions are sacrificed for basic communications. The trade-off is stark. You can talk to the spacecraft, receive its science data, send commands, maintain the mission. Or you can perform the time-intensive ranging measurements that tell you precisely where it is. Often, you cannot do both for every spacecraft that needs attention. The Artemis II mission nearly broke the Deep Space Network's operational capacity. The return of human spaceflight beyond low Earth orbit brought demands the network hadn't faced in decades. Continuous tracking requirements, high bandwidth communications, priority access that pushed other missions into secondary status. The network held, but the strain was evident. Tracking data quality may be compromised during high-demand periods. The system works, but it works at the edge of its capabilities. This isn't a story about failure. It's a story about the gap between public perception and operational reality. We speak about spacecraft navigation with a confidence that suggests absolute knowledge. We publish trajectory plots showing clean lines across the solar system. We announce planetary encounters with precise timing. And all of that is true in the ways that matter for mission success. But between those moments of precision, during the long cruise phases when spacecraft are simply traveling, there's uncertainty. Managed uncertainty, acceptable uncertainty, but uncertainty nonetheless. The spacecraft is out there, somewhere in a region of space that we've narrowed down to within 1,000 kilometers. In the context of interplanetary distances, being lost by 1,000 kilometers still counts as found. At planetary encounter, position is known to within 1 kilometer. The tracking intensifies as the spacecraft approaches its target. High-precision ranging sessions become frequent. The uncertainty collapses. By the time the spacecraft reaches its destination, we know where it is with the precision we always claimed. The encounter happens on schedule. The science data returns. The mission succeeds. But in the vast cruise between worlds, we're navigating with uncertainties we don't publicize. Trusting mathematics across distances where our margin of error would be catastrophic on Earth but barely registers in space. The Deep Space Network does its job remarkably well, but it does it under constraints that force choices about what we track and when we track it. The spacecraft are out there, following their trajectories, doing exactly what we designed them to do. And most of the time, we know where they are. Most of the time, the predictions match reality closely enough. Most of the time, the uncertainties don't matter. But sometimes during peak traffic, when the network is stretched to 90% capacity and controllers are making choices about which spacecraft to track, some probes drift in position uncertainties exceeding 1,000 kilometers. They're not lost. Not really. We'll find them again when we need to, when resources allow. When the next ranging session narrows the uncertainty back down. Until then, they're out there, somewhere, in a region of space we've calculated but not confirmed, navigating the solar system with a precision that's extraordinary by any reasonable measure, but not quite as absolute as the mission summaries suggest. That's the truth the Deep Space Network revealed when it nearly broke. Not that the system fails, but that it succeeds by accepting uncertainties we rarely acknowledge. And in the silence of deep space, 1,000 kilometers of uncertainty is close enough.